property we discuss here. So that three colligative property. First one, that is here the lowering of vapor pressure. Second one is the elevation in boiling point. Third one is the here the depressing in freezing point. Now we have to discuss the next colligative property that become osmotic pressure. So the osmotic pressure. Osmotic pressure. So look at here. So what discuss the next colligative property that is called as a osmotic pressure. If you consider the osmotic pressure, we know that that is the osmosis. We learn in here the biology what is the osmosis. So here if you consider the osmosis, to know the osmosis, so look at here the osmosis, the flow of the solvent particle through the semi-permeable membrane, this is a semi-permeable membrane, is called as a osmosis, or the flow of the solvent from lower concentration to the higher concentration. So look at here the flow of the solvent molecule from lower concentration to the higher concentration is called as a osmosis. So here what happen? Look at here, if this is a solvent, it is a solvent, and if you make the solution, here by adding the non-volatile solute particle. So if we add this non-volatile solute particle, what happen? It make the solution, and we know that because this is a semi-permeable membrane which allow only the solvent particle, so what happen? The flow of these solvent molecule is to be from solvent to the solution, or if it is a lower concentration and it is a higher concentration, it is from lower concentration to the higher concentration. Now if we consider here, that is here the pressure which is to be applied from the solution side, to stop the flow of the solvent molecule, that pressure is called as a osmotic pressure, or the pressure which is to be required to stop the osmosis is called as a osmotic pressure. So look at here, this pressure is to be depend upon the number of the solute particle which is to be added here. If the maximum number of the solute particle which is to be added here, maximum is the flow of that solvent particle from lower concentration to the higher concentration, and maximum is the pressure which is to be required to stop that osmosis, and therefore here it is depend upon the number of solute particle, and therefore we say that it is a colligative property. So the property which depend upon the number of the solute particle, that property is called as a colligative property, and therefore the osmotic pressure is also depend upon the number of solute particle which is to be added here. If the maximum is the number of solute particle is added, so maximum is the flow, and here maximum is the pressure which is to be applied to stop that flow, and therefore it is to be depend upon the number of solute particle, and therefore we say that the osmotic pressure is the colligative property. Okay, now here the osmotic pressure. So here if you consider here the osmotic pressure, if the solution having the same concentration, another solution is there, here solution, we make the solution, but its concentration becomes same, number of particle which is to be present in both the solution is the same, so no net flow is to be observed, such type of the solution is called as a isotonic solution. That is called as a isotonic solution. The solution which having the same concentration, that solution is called as a isotonic solution, or because of the that same concentration, here the osmotic pressure is to be same, and therefore the solution which having the same osmotic pressure, that solutions is called as a isotonic solution. Now look at here, if this is a solution and here this solution having the lower concentration, if this solution having the lower concentration, then this solution is called as a hypotonic solution. Solution which having the lower concentration, solution which having the lower osmotic pressure, that solution is called as a hypotonic solution. This is called as a hypotonic solution. Hypotonic solution. And the solution which having the higher concentration, the solution which having the higher concentration, this solution is called as a hypertonic solution. Hypertonic solution, or we say that the solution which having the higher osmotic pressure, that solution is called as a hypertonic solution. Solution which having the lower osmotic pressure is called as a hypotonic solution. This is a hypotonic solution, and if both having the same osmotic pressure, then we call it as a isotonic solution or same osmotic pressure. So in this way, three type of the solution we say that here the isotonic, hypotonic and the hypertonic. So the question which is to be asked in exam, so what happen if you take the cell, this is a cell. So here the cell, we know that cell membrane is a semi-permeable membrane, and if we put that cell in the higher concentration solution, so what happen, this cell is shrink, because the flow from lower concentration to the higher concentration, and the shrinking of this cell is to be take place. So here in this way the cell is to be shrink because higher concentration, higher osmotic pressure. Now if this is put into the lower concentration, this is a lower concentration, if you consider that, if it is the same concentration, at that time here the no net flow between these solvent of the cell and here these solvent, and if it is put into the lower concentration, then this cell is to be swell. This cell is to be swell because it's having the lower concentration. So what happen if the same concentration is there, at that time the no net flow between this cell and out of the cell here through the semi-permeable membrane. But if we put this cell here into higher concentration, at that time that shell become shrink because the flow of the solvent from that cell is come out. And here if you consider that lower concentration, if you put that cell, what happen, the flow of the solvent to the cell is to be take place and the cell is to be swell. So in this way here if you look at here the eggs is to be boiled. What happen, that eggs if having the higher concentration, at that time the flow of the water from water to the here, that is a through semipermeable membrane of the eggs is to be take place, and that break the membrane of the eggs. But if we boil that eggs into the here the salt solution, small pinch of the here the if we add salt in the water, what happen? The concentration of that solution to be increases, and therefore what happen? That eggs is not to be break its membrane. So in this way, here that is a osmotic pressure. Now, if you consider the osmotic pressure, here how to apply the law for the osmotic pressure. Here the in your syllabus, one of Boyles law, one of Charles law, one of Avogadro's law, and one of general gas equation. If he combines that, what happen? If you consider the here the one of general gas equation, here the osmotic pressure is to be represented by pi. Look at here, the osmotic pressure is to be represented by pi, and therefore generally we know that the pressure PV is equal to nRT is the general gas equation. In the place of the P, we have to use the osmotic pressure, that is the pi. So the pi V is equal to nRT. Pi V is equal to nRT. So here pi is equal to nRT upon V. So here or n upon V, we know that it's a concentration, number of moles per volume, or we say that the concentration. So here the pi is equal to CRT. So in this way, what happen here, that is we can use the osmotic pressure equation. So the osmotic pressure equation, from that we can calculate the osmotic pressure, we can calculate here the concentration, we can calculate the number of the particle which is to be added there, because in the place of the n we can use that is the weight divided by the molecular weight. So the number of particle which is to be added, that can be calculated here. So in this way, this is a equation by which we can calculate the osmotic pressure which is to be obtained by adding the number of the solute particle. That is also depend upon, that is the number of the solute particle. If the maximum is the number of solute particle, then maximum is the osmotic pressure which is to be observed here. So in this way, here the equation which is to be used in numericals, we discussed that the numericals which is based upon that the colligative property. So look at here. So if you consider the colligative property, we discussed that is the first colligative property, that is the lowering of vapor pressure, and the equation which is to be used for that, here the delta P divided by P naught is equal to here the X2, or the another which is to be used, the equation is delta P divided by P naught is equal to W2 divided by here the M2 into M1 divided by W1. This is the equation where we can use the for the lowering of vapor pressure, the another for elevation in boiling point. So we know that delta TB is equal to KB into molality. So here the delta TB is equal to K into W2 into 1000 divided by M2 into W1. So this is another equation from which we can calculate the numerical problem, or which can solve the numerical problem. So now the third colligative property, that is depressing increasing point, that is a delta TF. Delta TF is also equal to KF into molality, and therefore delta TF is equal to KF into W2 into 1000 divided by M2 into W1. So this is another colligative property by which we can calculate the molecular mass, weight, or the depressing increasing point. And the third colligative property, where the equation which is to be used for third colligative property is pi V is equal to nRT, or we say that pi pi is equal to nRT divided by V, or pi is equal to here n upon V, it means the concentration CRT. So in this way, here the equation which is to be used to solve the numerical. So you must be remember this equation. Now look at here, the also another equation by considering the font of Boyles law, pi 1, here the, if you consider here the pressure, we know that pressure is inversely proportional to the volume, therefore, and directly proportional to the concentration. So here what happen, here the pi 1 upon, here the pi 1 upon C1 is equal to pi 2 upon C2. This equation can be used. So here pi 1 upon C1 is equal to pi 2 upon C2. This equation which is to be used here, so by which we can calculate the here the osmotic pressure of the one of the solution. If you know the osmotic pressure of the other solution, so this is the another equation depend upon, that is there the Boyles law. Depend upon the Boyles law. We know that the temperature also, if we consider the temperature, we know that the pressure is directly proportional to temperature. Same way the osmotic pressure, if you consider that, which is to be directly proportional to the temperature. If it is directly proportional to the temperature, then we say that here there is a pi 1 upon T1 is equal to pi 2 upon T2. So in this way, these are the sum of the extra here the equation which is to be used, which is can be applied in various numericals. So in this way we completed the 4 colligative property. One of them is called the lowering of vapor pressure, and the lowering of vapor pressure, if you consider that here the this delta P divided by P naught is equal to x2. Then the equation which is to be used, the delta P divided by P naught is the relative lowering of vapor pressure. Delta T is equal to Kb into molarity. So we put the value of that. So in this way, by using these equation, we can solve the numericals. In next period, we discuss the one-off factor, because what happen, that is the number of particle which is to be added, that can be dissociate, that can be associated. So because of that dissociation and association, whatever may be the expected, the theoretical property which is to be here the required or calculated, theoretical calculated, that is not equal to the observed colligative property, and therefore because of that dissociation and association which is to be observed, and because of that number of particles is to be increased. So what happen, if the dissociation is to be take place, the whatever may be the particle which is to be here the present, that can be multiplied. Suppose NaCl is there, we know that NaCl, so we consider the NaCl as a one particle, but when it is dissolved in the solvent, it gives the behave like the separately Na plus and the Cl minus, and therefore the number of particle is twice, number of particle is twice, and therefore the whatever may be the expected colligative property by theoretical, which is not to be obtained here. So here the observed colligative property is different from that. So depend upon the number of the solid particle, here the colligative property is different. In next period we use the idea about that is the one-off factor. So one-off factor is nothing but the observed colligative property divided by theoretical colligative property. So that point we discuss in next period. Here we stop. Okay.